Hopefully everybody is able to be nice and warm at home. Everybody can hear me just fine. Okay, great. Now, I was messing with my audio devices, which occurred to me 10 minutes ago was a great idea to be doing that before my class. I'm trying to figure out how to stream my DAW to my audio output so that I can stream it over Zoom or more importantly Discord, so that I could show off my new instrument. But it's a headache, or not my new instrument, but my new instruments that I play using this instrument. The world of music, of electronic instruments, is mad, and expensive and overly complicated. All right, so let's go ahead and get started. Harvard, boom. Okay, Harvard data structures practice final. Okay, and I don't think I have anything too embarrassing on my screen. Okay, so let's go ahead and share. Oh wait, no, my desktop isn't fully clean. Ah, how embarrassing. Okay, so all right, so we were going through this one. So we have these Dijkstra's algorithm. That's where we were, or not Dijkstra's algorithm, but these graph algorithms. Okay, so let's go ahead and work on this. So we want to perform a depth. So on our actual exam, you will be required to perform either a depth first or breadth first search, or breadth first or depth first traversal, and you'll be required to do Dijkstra's, regardless of what the other one is. Get used to the fact of, as a computer science student, that every time you learn Dijkstra, you'll be tested on it in an exam or a final exam. It's just, so learn it now, get comfortable with it, and you've got basically a free batch of points on every single final exam you take from here until you graduate. Okay, so depth first search traversal, we want to start from index from here, from C. Let's do it with a purple color. And wants us to do a depth first traversal. We want to select the smallest edge first when appropriate. So, right, if we're starting from C, we have 3 different paths we can go down, right, to do our traversal. So we need some way of breaking the ties. Personally, I like to do that alphabetically, but for this exam, it says it wants to use the shortest edge. So we have 5, 22, 30. So the smallest edge is B. So I'm going to go and keep track of the way the algorithm does it here. So we're starting at C. We sort our edges in, and so then we go to B next. Okay. List the vertices in order they are visited. So B has some edges. It does have a short edge on going to C, but we've already been to C, right? That's where we came from. So our other edges are 18, 22, 17, and 13. So we're going to select the 13 edge and go to A. A has 2 edges, 13 and 10, but we've gone to the 13 route, so we go down to the 10 to D. And D has a edge to B, but we've already been there, so there's no need to go to B, right? This traversal. So we back out. Now we back out to B. So now we're at B again. Okay. So from B, where are we going to go? We're going to go to 18 or 20 are our two choices. So we'll go to F via 18. And then now we're at F, but there's nowhere to go from here. So we pop our stack and go back to B. And then we go down here to E. And then we're done. And then we go back. Gets a bit messy if when I draw it, but that's our answer. Okay, breadth first traversal is a bit easier, right? In fact, we can just simply use our queue and our set of visited nodes. And the queue will double as our scene, because if it's in the queue or if it's in visited, then we don't want to revisit it. So we're going to start at C, and again, break things in the order they appear. But with breadth first, we select all of our neighbors and we just put them into the queue in the order we want to visit them. So we've been to C, and we want to go to B, E, and F. So first things first, we're going to go and travel to B. And then we see that B has 5 neighbors, 2 of which we haven't been to. So we put those 2 into the queue. We'll put in A first because it has the shortest edge, and we'll put in D after that. Okay. So next we travel from we visit E, which has no additional new neighbors, then to F, then to A, and then to D. This is breadth for. In other words, what did we just do? Well, we started at 0 steps away, then we went to all the things that were 1 away, and then all the things that were 2 steps away. That's breadth first search. Dijkstra's is essentially breadth first search using edges, by the way. That's theoretically what it comes down to. Prim's algorithm is for minimum spanning trees, but it's not something I covered. I thought it was more fun to cover topological sort. Okay. So the shortest path from D to E, we want to find the shortest path from here to here using Dijkstra's algorithm. This is probably going to be the last theoretical thing I'm going to go over before we go on to coding. Okay. Okay. So Dijkstra's algorithm, we are going to basically create a, Dijkstra's, okay, sorry about this. Dijkstra's algorithm, what we're going to do is we're going to need to create our table just like the computer would. That is the easiest way to do it. Okay. Which is that we need the nodes. So A, B, C, D, E, F. Although since we're starting from D, let's go ahead. Well, what we need here is the node, and then we need the distance and the predecessor. So in other words, how far away the node is from us, and where and how we got there. So we can already fill that in for D since we're starting at D according to the instructions. I'm starting at D, and D's predecessor is nobody else. So I can either put a 0 or a dash there. And then I'm going to initialize my my distances. So D has distance to, so we figure out what the distance is from D to everything else. D has a distance from, what's the cost to get from D to A? It's 10, and I'm going there from D. What's the cost from D to B? It is 17, and I'm going through D. What's the cost to get to C? There isn't a connection, so it's infinite cost, so it's impossible to get there. And same with the rest. The rest are infinite costs. Make sense? That's the way Dijkstra's work. We put down an infinite cost. All right, now for our next step, what are we going to do? We are going to, we need to basically figure out which of these was the shortest, has has the shortest distance. So 10 is the smallest out of all these. So we found the shortest path to A now. Okay. So is there any new information that that starting from A gives us? A has this edge that goes to B, which has that has a cost of 13. So the question is the cost to get to A plus 13? So it's 10 plus 13. Is that cheaper than what we already know to get to B? And the answer is no, 23 is not. So that doesn't update the graph. D to B. Sorry, next we have 17, infinity, infinity, infinity. So D to B, that's the cheapest path to get to B. Okay. So what we need to know now is from B, what new edges are exposed. We have B to C. Okay, so is the cost to get to B plus 5 greater, is that less than the cost we know to get to C? Well, that's 17 plus 5, that's 22, that is less than infinity, so put down 22 here, and say we can get to C from B, and the total cost is going to be 22. And then we do the same things for E and F because they have infinite costs as well, where we're going to say B is the cheapest way to get to these guys. So B, so E to F, so sorry, B to E is 20 plus 17, which is 37. I am mildly distracted by the fact that I hear a child on the stairs. And then B to F is 17 plus 18, which is 35. Okay. And this graph isn't a particularly, this doesn't do much with Dijkstra's. It doesn't change too much, I don't think. So next we look at the cheapest, C. Does C give us any new options? It gives us to 30. 30 plus 22 is not less than 35. And then E would be, and then F would be next. And it doesn't give us any new information, nor does E. So that's our final graph. Okay. So, okay. Suppose you want to print a binary tree in reverse level order, like below. Okay. So, it's asking for reverse level order. Print a binary tree like the one shown below in reverse level order, so the labels of the node in the tree would appear in the reverse alphabetical order. You may use his stack a queue. So this is a change from the last time he did this. Last time he just wanted an algorithm that printed out everything in level order. So A, B, C, D, E, F, which, if you've been paying attention, that is just breadth first search. So this is saying, hey, can you print out a reverse breadth first search? All right, so I want you to put on your trickster hats here. What is the easiest way to print this out in reverse breadth first search order? And remember, think like a trickster here. Be obnoxious. Depth first searches would not. Katrina has it. Just put it in order and then print it out backwards. That's fair. Yep. Oh, Aaron, yes, then correct. Yes, you could do your breadth first search and then put it into a stack. Yeah, let's just get it in. Let's just do normal order and we'll take our answer and print it out in reverse. That's all you need to do. It's fairly straightforward. So let's go ahead and just kind of show. So it's just doing this before one extra step. So let's go ahead and create a, I'm going to create a public class, public static, public private static. Yes, I know I'm screen sharing. Class tree node. Private second. Okay, and that doesn't need to take in it. Class tree node, and it's just going to have a tree node. I'm just going to call it tree node here. Left. Can I make the screen bigger? 1 second. What do you mean by the screen? Do you want me to up the size of my font? Easy enough. Hey, do we have... Do you have MS? Yeah, whatever. That should be nice and easy to read. Tree node left. Tree node right. And that's all we need to do our algorithms, right? So public, static, void. And that's all we need to do our algorithms, I should say, so that we can write this and it won't throw any errors at us for missing any variables. Reverse BFS. It's just going to print everything out, and it's going to take in tree node. Right, and so let me just take a look at his data structure. Pseudocode. Oh, he just wants the pseudocode for it. Ooh, that's boring. I'm still going to write it. Okay. And then I'll bring up the one that I thought was interesting from the other one concerning hash maps. So for reverse BFS, what do we do for that? We will just simply have to do BFS on the nodes. Now BFS requires a queue. So queue of QE is equal to new. Do I get to do is queue's actual thing? No, I would have to new linked list. So queues are interfaces, and I can implement it using a linked list. Awesome. So, and that's all I need to do. Because breadth first search of the way it works, it needs to be done in a in the form of we can't do it recursively. So what we're going to just have to do is deal with that. New. And here I'm going to do a linked list for reasons that will become very apparent very quickly. Okay. So we have our two data structures that we're going to need to use. We have our queue, and then we have our output. Okay. And now what we're going to do is queue.offer our root so that it started, so that we have something for it to have to begin with. It's not a queue of E's though, it's a queue of tree nodes, right? Mistake there. Okay. There, now it's happy. While queue dot is empty, and that is not true. While there's stuff in the queue. Now, unlike most breadth first searches, we don't actually have to care about whether or not we've seen anything because it's a tree, and trees specifically mean there's a specific order that these things are going to go in. And so there's no risk of us doubling back or anything special like that. So tree node e is current is equal to q dot pull to get the top thing out of it. We're going to go ahead and take the output dot add, but here's what I'm going to do. I'm going to add 0, and this will effectively put it in reverse for us. Current dot item, and that's why I'm using a linked list, so that this is this is a constant time operation. But if I take a collection and add things to index 0 consistently, that's going to reverse it, right? If I do hello, that's going to be HE, it's going to be H, then EH, then LEH, then LLEH, and then OLLEH. So, okay, and then to keep it going, what do? We just need to do q.offer, if current dot left is not null. So here we're going to do our null checks as opposed to otherwise. If current dot left is not null, if current dot right is not null, output dot add, not output, q dot offer current dot left. And now, just to finish it off, all we have to do to print everything is for every E item in output sout item. Okay, we're done. Okay, so now let's move on to the what I consider the next interesting question. Okay. Which is not on this exam, and it's suppose I have some I have a file. This is from something else. So suppose I have a file of item, and I described it last time. Suppose I have a file of usernames and login times. So I'm going to use Alice and Bob because Alice and Bob are A and B, right? And Carol, we'll use her too, and possibly Dan. So Alice 1001, Bob, Alice, Bob, Dan, Carol, Alice, Bob, Edgar. So suppose I have a file that looks something like this. All right, where we have username, okay, pretend it's a username and not actual name, and numbers representing, so we have username, and then time in seconds for session. So these are this is a file containing, hey, Alice was logged in for 1001 seconds. Bob was logged in for 2131 seconds. Alice was logged in for 21 and 34 seconds. Makes sense what the file consists of? They're just login times for each user. Make sense? Okay. So now what I want to do is I want to write a function that computes the average amount of time for each user. The average amount of time that each user was logged in for. Okay. And I'm going to pretend that there's a file exists. I'm not going to actually test it out, but I could. But I'm fairly confident in my abilities. So now I like this one because it is fairly large, but fairly understandable. Public static. And we're going to want to return a map specifically of string to double, where the string is the user and the double is going to represent the average amount of time they spent logged in. So we have all these individual sessions, okay? I'm really great at typing today. Get average session length, and it's going to be a string file name as our input. Okay. And then we're going to need return this map. And as always, I'm going to put a return null here so that we're going to have some output. Now, and the only hint they give you here, but I think it's fairly obvious because I've done this a lot of times, so don't feel bad if it's not obvious to you, is that to compute the average of something, what do I need? I need how many times it occurs and the values for each occurrence. So in other words, for each user, I have to do two things. I have to count the number of times that Alice has a login session, and then I also have to figure out how many total sections she was logged in for. Make sense? So for that, I'm going to use two maps. Map string to integer num logins is equal to new, and we'll go ahead and use a hash map. And then we'll do the same thing because we're dealing with integers over here. String to integer, and that will be total login time. Make sense? Okay. But now we have to actually, but before we can start doing that, I have to read this file. So I'm going to basically not worry about this map part because I have to get this data from this file in a way that I can use. Okay, which is going to require a scanner. But let me think about how I want to store the data. I want to store the data. Probably not. Let's see. I can either store the data, you know, just as a bunch of strings and analyze the strings. But if I'm already going to go through this, can I just? I'm just thinking about if I should split it up and use an intermediary data structure. Nah, don't need to use an intermediary data structure. So let's go ahead and just work on opening the file so we can read it. Right, because what we need to do is read the data structure and we'll populate this. That's our second part, which is actually using these to generate. So scanner is equal to new scanner. And rather than doing system.in, what we're going to do, we're going to say new file name. Boom, boom. And it goes, oh my God, I don't know what a file is. And then it's going to go, oh my God, you can't do that without try catching it, because if you do try it without try catching it, you're a terrible person. Okay, fine. So we're going to try to do it. So we're going to try, we're going to listen to the IDE and Java and put in a try catch. So scanner is equal to new file name scanner. So this will crash when you run it because the file doesn't exist. That's fine. Or it's not going to crash. It's going to actually go over here and num logins and total login time will be empty. So if you want to actually test it, you'll have to make your own file and pass it in here. Okay. So scanner is equal to new scanner. So while, and the way I like to read anything with scanner is never to use hasNext, but always use hasNext line. While scanner.hasNext line, and then I want to read the line. Always, and then once I have the line, I can parse it however I need to. And parse it I must, because we've got a Bob and this. Now, fortunately, with this, we know that the formatting of it is 3 parts. It is Alice and sorry, it is username and then space and then the login time, which is great. So what we're going to do is that we are going to say string array fields is equal to, because it has two, it will have two fields, line dot split. And it wants a regex, but honestly, we don't really need to. Honestly, we can just do that and we're good. Split on a space. And it will. No need to do anything more fancy other than that. So now we've got two fields. Field 0 will be this. Field 1 will be this. So now we can actually start populating our data. String username is equal to field 0. And then int login time, or int, let's go with int time is equal to integer dot parse int, and then it needs the string that we want to parse, fields 1. That will turn that into an integer. So we've now got our integer and our field. So now what do we need to do? We ask ourselves, hey, if if not num logins dot contains key username. So in other words, if I've not seen this user before, then what do I want to do? Now I've seen her once. So num logins put username, I've seen them once. Otherwise, I'm going to be verbose here. Int prev is equal to num login dot get username, and then num logins dot put username prev plus 1. Okay. Well, what about total login time? Do I have to do this entire nonsense, this double block for total login time as well? And the answer is no. So first off, right, num logins just counts the number of times I've seen this username. Great, that's what I did there. Total login time counts the number of seconds. But fortunately, we know that these both will have the exact same keys because it's over the same data set. And if I've seen Alice, then there's no reason it, right? Once I see Alice once, it's going to make sense that she's already in the other field. So all I have to do is, if I haven't seen her yet, total login time dot put username and then time. And now over here where I haven't seen her yet, I'm going to change this to prev count and int prev time to total login time dot get username, and then total login time dot put prev time plus time. Making sense to everybody? And this is why I say it's a bit longer, because that is a lot of lines just to simply get your data. But now we've got our data. Okay, so now we've got our data. We've got for every person the number of times we've seen them and how long they've been in there. So now we need to do our output map, which is map string, and I'm doing double because we're going to be doing division, so that makes sense that we'll want to keep that. Double average is equal to new hash map. And now what we do is that we are going to iterate through our keys and return this average. For string username in num logins dot key set. So that goes over all the keys. And remember, every key that exists in num logins also exists in total login time. So what we're going to do is for each user, we're going to calculate that average. Okay. And we'll just simply do this in one line because I can. Average dot put username. And then we're going to do right, it's going to be the total amount of time they've been logged in for. So total login time dot get username divided by num logins dot get username. Right, because that's what the average is. It is the username and then this, and then it's not liking me for some reason. Why don't you like me? Requires type double and provides a type int. Right, because this is just the thing with the way generics work, is that if and wrapping, I'm providing an int primitive, but it wants a double object. So I can convert a double primitive to a double object. So I'm just going to do 1.0 times, and that actually takes care of the whole thing. It's a little silly, but that's the easiest way to deal with that. Okay, that one, I liked it, even though it's a bit longer than what I would put on an average final exam. But I like it because it's got a lot of moving parts there. Okay, let's see what else was in here. We had linked lists, but we've already kind of dealt with linked lists. Did this some nasty stuff on exam 1. Going to go ahead and refactor this, rename it into Node. Isn't that cool? Love being able to do that. I'm just going to call it Node to make it shorter, because we do have a nice, we do need to practice our recursion here. Okay, rewrite the search so it uses iteration instead of recursion. Not necessary. Fun. I like this one. This one's fun. One of my favorites. In fact, something like this has been on the final exam. Something like this was on the final exam that we gave out around 5 years ago. So, in terms of difficulty that we aim for, this is around where we find that a higher end of difficulty. If in terms of creating the code for it. So write a Java method called mirror that takes a reference to a root node of a binary tree and creates a new tree with its own nodes. That is the mirror image of the original tree. So for example, if I pass in this guy 1, 2, 3, 4, 5, 6, 7, then the new tree that we construct is 1, 3, 2, 5, 4, 7, 6. And notice that basically not only have I swapped my left and right childs, but so it's also swapped everywhere. Make sense? Everybody follow the kind of concept? So, okay. So you get this problem. And this is not a rhetorical question. I want a serious answer here. This looks complicated. Where do you begin? When you see a complicated tree question that says it's going to probably be much easier with recursion, where do you begin?
The base case.
The base case. That is what I wanted to hear. Always start with the base case, because once you get to the base case, remember, recursion's all about being lazy. It's about breaking it down so it's just local decisions, okay? Base case. What do I need to do for my base case? Okay, so let's write this. Public static, it's going to return a new tree, so node e public static E node E mirror node E root. Okay, cool. And we'll want to return null. Actually, yeah. I'll return myself right now. Okay. That seems like I'll return myself for right now, but no null because okay, let's start out. So base case, what is the base case? Good easy base case. If root is null, that's the easiest thing, right? If root is null, then I don't want to do anything, right? So I need to create a copy of null, which means return null, right? The mirror image of nothingness is more nothingness. Make sense to everybody? Okay. So I'm feeling pretty good so far. That's worth a couple points at least, yeah. And it is because you recognize that you recognize with recursive problems you need to start with the base case, and you've created the correct base case. That is definitely worth at least 3 points. If it's a 10-point question. So, and then you could just say, so if I get this if I see this turned in, by the way, on a 10-point problem, that's going to be 3 points. Just FYI. You know, because you got the general idea of how this is going to go. So let's not hand wave it at least. So, so in that case, what do I need to do? So if I'm not null, it wants me to create, well, I need to make a mirror image. But honestly, if I'm starting at 1, to make a mirror image, it wants a new tree, which means I need to make a new version of myself. Let me worry about swap this whole mirror image for my children later, right? So node E new root is equal to new node, and I didn't put in a constructor, so I'll have to do so now. Node root dot item. What am I doing? Okay, let's go ahead and it's like going, no, you've made a bad call here. Yeah, let's fix it by creating that constructor. That's all I was waiting for. Being lazy. And now let's go ahead and return new root. Okay, that's worth 1 more point, I'd think. Because I've recognized, hey, otherwise I want to create a copy of myself. But this new copy, he needs kids, right? I've got 2 and 3. He's going to want 3 and 2, right? And so, but he's going to want copies of them and themselves. But we can get to that. Actually, thinking to myself, wait a second. I'm going to want 1 and I'm going to want 2 and 3. He's going to want 3 and 2, but they're going to need copies. But if I call this method, it gives me a copy. And there, 2, if we look at this subtree starting at 2, right? It's also been reversed, right? 2, it becomes 2, 4, 5, 6, 7. Sorry, from 2, 4, 5, 6, 7, it becomes 2, 5, 4, 7, 6. So that obviously has the mirror call applied to it. And you think to yourself, wait a second, recursion's easy, but can it be this easy? And the answer is always with recursion. So new root dot left is equal to is equal to the mirror image of my right side, right? And new root dot right is going to equal to the mirror image of my left side. I think that's actually just about it. All right, I created a new node. I said, hey, my left side is equal to the flipping of my right side. And the right side is going to be equal to the flipping of my left side. Right? So I'm saying reverse 2, 4, 5, 6, 7 and put it over on my right side. And then reverse 3 and put it on my left side. And what if I hit a null point? Oh, just give me a null because that's it. Does this make sense to everybody? And again, all this works because all I'm doing is just flipping the left and right nodes. That's all I'm doing. Yeah, with the node constructor, you just have to build, right? Node item is equal to this side item is equal to item. You just got to put an constructor in the node class. I renamed it tree node, by the way, simply just to make it easier for me. Okay, while you're looking at that, I will, okay. Aha, one of those questions that I love to ask. What is the runtime of your mirror method? Use big O notation and explain why briefly. It's O of n because we're making one copy of every node. And then, yeah, we're switching the orientation of what points to it, but honestly, that's just a factor. That's like 3n, which becomes O of n. You know, we're not re-going over any nodes, nor are we just doing a subset of these nodes. Okay? Now, let's go ahead and GitHub Classroom. Let's go back to our study guide. And look at some more questions with regards to theory. So these here are theory questions. And then, see, are you still up? Yes, you are. More theory questions. Okay. But theory questions are good for you. That is, you know. Okay. So this is more if you've had a formal algorithms kind of thing. But let's go ahead and look at this question. Consider insertion sort and merge sort. Okay? For each algorithm, what is the worst case asymptotic upper bound on the running time if you know additionally that the array is inputs already sorted, reversely sorted, or the input is n copies of the same number? For each case and each sorting algorithm, state your answer and justify it in one sentence. Okay? So, right, let's consider merge sort and insertion sort, right? It's asking what is the runtime? What is the worst case runtime if we know more facts about the input? Okay. This is fairly easy for merge sort. And I like that question because it's kind of making you double think. It makes you take a quick second look. But with merge sort, the runtime is always n log n. It doesn't matter. It's always n log n. That's the thing about merge sort. right? Right over here, worst case complexity, average complexity, base complexity, right? Right. Again, Wikipedia is kind of actually great for these kind of things because, I mean, do you get these in textbooks? No, you do not. I'm totally stealing it and putting it in my textbook because it is Creative Commons. All right. So, best case performance is never going to be better than n log n. Or so again. So if we know that it's actually it says O of n in natural variant. What is natural variant? It says if we're using a natural variant of sort of merge sort, like say Tim sort, then yes, we can get O of n runtime if it's all sorted. But we're just considering canonical merge sort here, right? Regular merge sort, which doesn't look at the items. It just splits them and splits them and splits them and puts them back together. And when you're using a single processor, like we're doing here, which is always the assumption we're using here, because that changes if you have multiple processors. If it's no matter what, it's always going to be n log n here. So insertion sort, that changes. Worst case scenario, insertion sort though, the reason merge sort is able to do a O of n runtime on its quote unquote natural variant in Tim sort, right, is because it uses insertion sort or concepts from insertion sort. Insertion sort has O of n best case, n squared worst case. And in fact, we've got those cases here. If it's already sorted, right, then it takes O of n time to do insertion sort, right? Let's go ahead and take a look at that, right? If I have 2, 5, 7, 15, 83, 109, 552, right? The objective is that, okay, I need to insert 2 into the sorted portion of the array, or I start with 2 being the sorted portion of the array. Now I need to insert 5 into the sorted portion of the array. Done. Need to insert 7 into the sorted portion of the array. Done. 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 No need to swap anything. We just go through and don't bother inserting anything anywhere. So best case scenario, O of n. What if it's reversely sorted though? That's actually the worst possible scenario. 5, 4, 3, 2, 1. So 5's been inserted, but now I have to take 4 and I have to swap it with 5 so that I can move over here. Then for 3, I have to put that in front of the 5 and then in front of the 4. Then for the 2, I have to put that in front of the 5 and then that in front of the 4. And then that, you get the idea. For each item, for the nth item, I'd have to move it n minus 1 times. So it's 1 move, then 2 moves, and 3 moves, and 4 moves, and 5 moves, and 6, then it's n squared. Okay, this one's possibly the most interest. The input is a list containing n copies of the same number. Yeah, so my list is this. And this is just a weird edge case of A, right? This is already sorted. 5s are sorted. It's already sorted. No need to do anything else, right? That makes sense to everybody? So that's also O of n. Okay. Let's see. So suppose you have a set of numbers where you over some time period do a constant number of insertions and a linear number of lookups of the maximum. To maintain your set of numbers, you can use either a heap or a binary search tree. A, assume you're interested in minimizing the average total runtime over the period. For each structure, what is the asymptotic upper bound for each average case runtime? So, okay. So here, what we're saying is that we are going to do some constant number of insertions, right? So we're going to add numbers to this set. They do the same performance here. So there's going to be no difference in performance here because both trees and heap, to add a number, any number is going to take log n time for any number. And we're doing a constant number of them. And so it's the same for comparison's sakes. I'm going to ignore this part because it's going to be the same for both of them. But what we have is some kind of linear number of lookups of the maximum, which I assume is the maximum number in the stored set. Okay? In which case, using a heap, specifically a max heap, is better. If we're using a binary search tree, right? The the item is going to be all the way over here to the right, and it's going to take log n time to get it. But if I'm looking up the maximum in a max heap, it's always at the top. So that means for a linear number of lookups, that means I'm doing n lookups. So for heap, it would just be n constant time lookups, so it would be O of n, versus n log n lookups. So for A, we definitely want to use a heap. Suppose you're actually interested in the worst case. For each structure, what is the asymptotic upper bound on the worst case runtime? I'm not going to change my answer. I don't think. Because on average, yeah, I'm not going to change my answer. I think my logic still holds for the worst case and the average case. And if I'm wrong, please correct me. Excuse me, I might need to take this. Oh, it's one of those scams. Hold on a second. Hi, you should be very disappointed in what you do for your life. Your mother would be disappointed in you. They don't stop calling me. Anyway, best thing you can do to them is, I don't know. Any kind of scammer is the worst. You don't take money from people. It's okay to. It's just not okay. It's just thievery with extra steps. All right. So let's see. Let's move on to this one. This is the one that I really like from this. Suppose you have a hash table and have inserted some elements. When you inspect it, you see the result looks like the picture below. Being a good student, you realize the picture is the problem. Sorry, this is a problem. So this is a hash table. We've inserted items into this hash table, and it looks like this. So first off, let's start off. What is the collision? What is the collision resolution strategy that we are using here? Anyone? What is the collision resolution? Chaining. Great. Chaining. That's right. So this is using chaining as opposed to open addressing. So what is the problem with our hash table? You can unmute if you want to answer, by the way. You don't have to put it in chat. Anyone? I know some of you are typing very furiously, I bet. But I can't see like person is typing on the screen like it can in a normal chat window. Really should add that as a feature to Zoom. That's why I say unmuting is much quicker. So what is the goal of a hash table? It's to kind of spread everything out, right? Are these spread out? Now we've got lumps, we've got clumps, we've got giant big clusters of items, right? Right? In fact, there are only 2 items that have had no collisions. All the rest of the items have had collisions. We have tons of collisions and a bunch of unused sets. A bunch of unused chains. So give an example of a hash function that could give rise to this behavior. And I'm taking it that you're all shy this morning and I want to make the best of our time. So if we notice, and it took me a bit of time to notice this, but is there any patterns here? You will notice that it just takes, again, just a bit of time, but the ones place for all the items are the same for each bucket, right? All the zeros went into 0, all the ones went into 2, all the 2s into 4, all the 3s into 6s, and now that I'm saying that out loud, 0, 0, 1, 2, 2, 4, 3, 6, 5, 10, 6, 12, right? Must be doing something by 2, right? It's a relationship of 2. So we can what is a operation that is what is doing this? So a hash function, not necessarily the hash function, but a hash function that would give us this. I could do x mod 10, get the ones place, right? And then, just to be clear about my order of operations, right? I'm going to multiply by 2. So, and that will give me the key I want to put anything in. So what would be a better hash function? Anything. A good hash function, though, reduces collisions, and thanks to magical mathematical properties, which we don't have time to get into here, but are covered in your textbook, I believe. If I do a prime number like this will lead to less collisions. So if I instead do x mod 19 and just, this spot's going to be empty. But even if I did x mod 20, that would probably spread things out pretty well. Because this would go to the 10's place. This would go to 15. Right? 26 would go to 16, and so on. You can already see that it's going to be clearing up a lot better. Okay. I also like this question over here, problem 7. Suppose that we insert an item X into a binary search tree that does not already contain X. Okay? So we're going to add an item to a binary search tree. The item isn't already in it. Suppose we then immediately delete X from the tree. Will the new tree be identical to the original one? So this is the classic, if the tree falls in the forest and then somebody puts it back, did it ever actually change? I think I'm mixing my metaphors a bit. So it's not asking philosophically, is it the same tree? Because philosophically, we could argue all day about the ship of Theseus and all that stuff. It's just saying, hey, if I did an equal statement on the past state and the current state, would it be true or false? Okay. And if yes, give the reason in no more than 3 sentences. If no, give a counterexample, draw pictures if necessary. There is no counterexample unless it's a binary. If it is not a... So, this depends on whether it's a self-balancing tree or not. If it's a self-balancing tree, all bets are off. Easy counterexample, it needed to rebalance itself. Like, for instance, a self-balancing tree, if I did one, just an easy example to show you, if I had 1 and 2 and then added 3, it would want to rebalance into 1. Sorry, it would want to rebalance into 2, 3. And yes, we didn't cover rebalancing trees, but that's fairly easy to see how that would work. And then it's fairly easy to see once we delete 3, it's a different tree than the original 1, 2. It's now 2, 1 to the left. So, but that's only if it's a self-balancing tree. If it's just a regular binary search tree, then the answer is yes, it's identical, which I assume is what they're going for. Yes, it's identical because if I've got some tree, so there's my subtree, there's my other subtree, right? If I add a node somewhere, where's it going to go? If I add an item somewhere, where does it go? It becomes a leaf. So it could go here, it could go here, it could go anywhere. It's just got to be hanging from the bottom as a leaf. And then if I remove it, what's going to happen? If I remove it, well, I need to delete that item. And deleting a leaf just simply removes the leaf. That's it. No changes to the overall structure for the tree. The only changes to the overall structure to the tree, a change only occurs if I delete something that has 2 children. And then that's when the structure changes. Okay. As you can see, this is coming from a much more mathematically focused class. Okay. So let's go ahead and look at, let's see. Let's see. All right. 2 conceptual questions about quicksort. The most common divide and conquer sorting algorithms are quicksort and merge sort. Now, they're divide and conquer because we recursively split them into left and half rights, and we divide it into left and half sides, and then conquer them individually. So, in practice, quicksort is used for sorting data in main storage, e.g. RAM, rather than merge sort. Give a reason why quicksort is likely the preferred sorting algorithm for this application, for doing things in RAM. Any suggestions why people might prefer quicksort over merge sort often?
Because it is done in place.
That's a good answer. Yes, because it is done in place. It doesn't require any extra memory. So, whereas because your RAM, remember, is a limited resource. And if I'm trying to sort a very, very, very large thing using merge sort, there's the risk that the auxiliary space might go over my allotted amount of RAM. Whereas the quicksort, well, if it's been allocated, I can use it and sort it. Boom, done. Okay. That is one reason why. And the other reason is because, but yeah, that's pretty much it, actually. Quicksort. Worst case running time, O of n squared, but as expecting running time of n log n, if the partition function works well. What needs to be true about the partition function for the running time to be O of n log n? And how can we, okay, so that's the first question. What needs to be true about the partition function in order for the runtime to get to n log n? So the partition function, go ahead. I saw.
Do some of the numbers have to be above and below, so it's not like you don't have all the numbers that are up and all the numbers that are down?
That's exactly correct. That is exactly 100% correct. We need to ensure for the partition function to work well, the pivot needs to be somewhere close to the median. That is the way that we would mathematically describe it. But yes, making sure that there's a balance between the number of numbers above and the number of numbers below. So choosing a median value. So as long as the pivot is a median value, that's great. In practice, how do we ensure that this happens? Because we can't always just hope that the median value is going to work. So how do we ensure that it happens? What we can do is that we can, for every, right, if I've got an array, I can, rather than just selecting the first item as the pivot, I can say, hey, compare these 3 items. Okay. And then sort them and move the middle item over here. So that way at least one item is going to be above. The idea, or take some representative sample, like 3 or 5, to make sure that that is the case. That is one way to ensure that you've got a median. In other words, just take some selection of items and get the median for that, and that's probably going to be closer to the median than just randomly picking. And since it's a constant number, it's going to be a constant time operation. Okay. Just looking at the amount of time we have left, I'll probably end up I'll go over this exam independently, I think, in its own video I'll do during the weekend or the study days. But so let's go back to this one and talk about some other just math heavy thinking problems. Okay. So suppose we have a heap. Oh, I remember this one, and I always forget. I remember doing this one. I remember figuring out the answer, but I never remember what it is. Okay, suppose we have a heap and we have 2 values, such that all the values are and 2 values. So we have a heap, and we also have 2 additional values, and they're all distinct. Let H12 be the heap if you insert 1 and then V1 and value 2 into the heap, and 2, 1 if you insert V2 into V1. Give an example of H where V1 and V2 such that if you insert them in different orders, you get different heaps. Okay. So you can't just start with the heap being empty. That won't work. So let's go with what we need to do, I think, is have it at a breakpoint like this. So let's do a minimum heap. So, and choose values that are easy to have higher and lower values. 7 and 10. So, oh, this is fairly easy actually. 11, 12, and then 7, 10, 12, 11. Okay, that was easy enough. The key to these problems are giving you an initial configuration that is useful, like having values where you could have values that are both above or below and the like. Okay. Suppose you have a graph like, I like this one. Suppose you have a graph like this one. And this is what something like in a social network might look like. The dot signifies some part of the graph that you don't know exactly. Not a straight link, though. Right? You know, however, there are many paths from the start to the goal. You also know that the paths tend to be rather long. Suppose you want to implement a program that searches for a path and returns the first one it can find. You have no need for finding the best path. You don't need to find the best path. You just have to find a path. Would you use breadth first search or depth first search as the basis for your program? Justify your answer in at most 2 sentences. So we use breadth first search or depth first search. And it's asking if we ran breadth first. Another way of viewing this: if I ran breadth first search and depth first search on 2 computers that are identical and have the same kind of randomization, which one would finish first? Breadth first search or depth first search on this kind of graph? And I see a chat. Depth first search. So what is the justification you have for depth first search? Because I believe that is the correct answer here.
Honestly, just going, I haven't studied them recently, but just going off the names, I would assume depth first search goes for depth, so it would go to the end first, while breadth would go through each
That's right.
in the first level.
Yeah. So the answer here is that if this graph is accurate, by the way, this means that basically we would potentially have to go through every edge in the graph to get to the goal, right? So if the goal, if basically all these paths have the identical the same identical length, then with breadth first search, I'd have to visit every single node in this graph. On the other hand, if they're slightly uneven, then, or we have some very short paths, some very long paths, depth first search will get there in minimum time, whatever the longest path length is, provided they are no dead ends. If there are dead ends, we'd have to backtrack a couple times and still get there. But with breadth first search, worst case scenario, we're potentially looking at visiting every graph. Depth first search does not potentially have to look at every, unless we're very unlucky and there are dead ends everywhere. But it's the reasoning for going through a maze. We're going to use depth first search because that's going to get us a path quicker. Breadth first search means we'd have to visit everything, and we might get lucky and get out sooner, but depth first search will most likely get us there sooner. One possible solution, though, I should mention, is that if I am starting pretty close to the goal, there is something I can do. Is that I can do, there's nothing necessarily stopping me from doing finding a path by doing breadth first search from both sides. So I could do one from start, one from goal, two from start, two from goal, and that can narrow in, and that can sometimes be useful in some edge cases. But depth first search for this answer, definitely. All right. So,